Hello class, this is today's audio version of the video about how to apply Cramer's rule and use inverse matrices to solve linear systems. So first we're going to start with Cramer's rule. Cramer's rule is just a method used to solve a system of linear equations, and the method involves using the determinants of matrices. So we've been working with matrices and calculating the determinants. So in order to use Cramer's rule, we're going to look at the situation when we're using a 2 by 2 matrix and as the coefficient matrix. So if I have a linear system written in standard form, the coefficient matrix is the matrix of the coefficients. So as we can see here, the coefficients of x are one column of the matrix, A and C, and the coefficients of y, B and D, are the second column of the coefficient matrix. Okay, so Cramer's rule involves finding determinants of that matrix, variations of that matrix. So let's say we have a 2 by 2 system, which means we have two linear equations with two variables. Then here the coefficient matrix is again the coefficients of x and the coefficients of y as the second column. If the determinant of the matrix, coefficient matrix, is not 0, then we can find a solution. And it's going to be exactly one solution. So how do we find the solution? Well, to find the value for x, what we're going to do is we're going to take the determinant of two matrices, the determinant of the original matrix A, which is going to be in the denominator, and the determinant of a modified matrix. The modified matrix has the same y column, BB, but then it's going to have a different x column since we're trying to find x. And that x column is going to be made up of the right-hand side in our linear system, our E and F. Okay? And that's how we use that to find x. To find y, we're going to use the same x column of the coefficient matrix, but the y column, since we're trying to find y, we're going to replace that y column with the right-hand side column over here. So we're going to find the determinant of that matrix and divide it by A. And that's how we get a solution. So let's take a look at an example. So here we have this 2 by 2 system with two equations, two variables, x and y. And in order to use Cramer's rule, the first thing we have to do is we have to determine the determinant of the coefficient matrix. Okay? So what is a coefficient? Remember the x coordinates, the coefficients of x and the coefficients of y. So here's the coefficients of x, and here are the coefficients of y. Okay, and as you can see, we're good to go. And then in order to figure out the value, we take the determinant, and the determinant can be used, just as we know, by cross multiplying and taking the difference. So negative 21 minus 4. So the determinant of this matrix is negative 25. And since the matrix has a determinant that's not 0, then that means we can use Cramer's rule to find the solution. So in order to use Cramer's rule, now we're going to divide our two matrix determinants by the determinant of A, which was 25. Okay? And then in order to figure out what the numerator matrix is going to be, we're going to keep the same y column, which is negative 2 and negative 7. And we're going to replace the current x column of the coefficient matrix with this right-hand side, which is for negative 4 and negative 11. And that's what's going to go right here. Okay. Okay. And we're going to find the determinant of that matrix. So positive 28 minus a negative 22, and we divide that by the determinant of the A matrix, and our current simplified answer is negative 2. So x is negative 2. We do the same process for y, but we keep the original x column, and we replace the original y column with the y from over here. Okay, and then we find the determinant of that matrix, which is negative 33 minus a negative 8. And we divide that by the determinant of the coefficient matrix, and we get positive 1. So our solution for x is 2, negative 2, 1. Okay, let's take a look for how we would do that in a 3 by 3 matrix. So Kramer's rule for a 3 by 3 system is essentially the same thing. The only difference is we have a larger coefficient matrix. So as we can see here, the coefficients of x for these three equations are a, b, and g. Coefficients for y are b, e, and h in this case. And the coefficients for now our third variable is c, f, and I. So again, we can only use Kramer's rule if the determinant of the coefficient matrix is not 0. So if the determinant is not 0, then we can use Kramer's rules. So the process is the exact same for a two-dimensional matrix. And that is, we're going to keep the original columns, but then replace the x column with the right-hand side column. So as you can see here, for the y value, we're going to replace the y column. And I call this the x, the y, and the z column. So I'm going to replace that column with this right-hand side and keep the original columns for the coefficient matrix. And for the z, I'm going to replace the z column with j, k, l, which are these values, and keep the original columns for the other variables. So now to figure out what x, y, and z are, we're going to have to take the determinant of the respective matrix and divide it by the determinant of the coefficient matrix. So let's take a quick look at an example. So here we're going to evaluate the determinant of this coefficient matrix, and as you can see, the coefficient matrix is going to be 3, negative 2, 4, 4, negative 3, 1, and negative 1, 4, 1, and all those values come from the coefficients of x, y, and z in the situation. So we know how to find the determinant, do a bunch of multiplications and add them up and then subtract them. And the determinant in this case is 61, which means that we can apply Kramer's rule because the determinant is not 0, which means we are going to have a solution. So in the denominator for each of these, it's going to be the same value of the denominator of the coefficient matrix. And then to determine the determinant of the numerator matrix, we replace the corresponding column with the right-hand side. So as we can see over here, the right-hand side is negative 1, 4, and 1. I'm sorry, I was totally wrong. The right-hand side column is 9, negative 14, negative 18. So if I go over here and see, that's what this column is. And the rest of the columns are from the same coefficient matrix. Over here, we replace the y column with negative 9. I'm sorry, why do I keep saying negative 9? It's 9, negative 14, 18. And let's see that. Sure enough, that's what we did over here. And for the z column, we replace the z column with the 9, negative 14, and negative 18. And we keep the other columns of the coefficient matrix the same. So when I do my determinants, in the interest of time, we're not going to calculate them one by one. We get these values, and when we divide them by the determinant of the coefficient matrix, we get a simplified answer, which doesn't always happen, but just in our case, in this example, it does. So our solution is x is negative 3, y is 4, and z is negative 2. Okay? So if you guys want to practice on your own, I provided the papers. And you can, if you want to know this answer, I'll just give you the answer already so you can check your work as well. All right. Now let's take a look at something else. So another way to determine the solution of a linear system of equations besides Kramer's rule is to use the inverse matrix to solve a linear system. So what do I mean by using the inverse matrix? So remember, if I have a system that looks like this, A, which is my coefficient matrix, times some x will give me my right-hand side. If I want to figure out what x is, which is the unknown in most situations, I have to get rid of the a. How do you get rid of the a? Well, normally we would divide if this was a set of numbers, but A is a matrix, not a set of numbers, and there is no division of matrices. So the reverse of how to get rid of A if we can't divide, well, we multiply by the inverse. Okay? So in other words, if I multiply A times A inverse, then this is what I'm going to have: A inverse on one side and A inverse on the other side to maintain the equality. But A times A inverse, from what you guys know, can be is the same thing as the identity matrix. And whenever I multiply the identity matrix by a matrix X, I get the original matrix back. So in order to figure out what X is, I get rid of the A by multiplying it by A inverse, and then I have to do that to both sides. So my X can be found by basically multiplying the right-hand side matrix B by A inverse. Okay? And this only works if the determinant of the coefficient matrix A is not 0. So let's take a look at an example. So here I have my situation. Here's my A matrix, and here's my B matrix. So I'm going to take my B matrix and multiply it by the inverse of my A matrix. So here's my A inverse matrix, and you guys remember that from last unit, how to find the A inverse matrix. So I'm going to take this, when I multiply both sides of my AX equals B by my inverse matrix, I'm going to be left with identity matrix on the left times X. On the right, I'm going to be left with this relationship. So that means my X matrix is really the same thing as what's happening when I multiply A inverse times B. And I'm only going quickly because this is a little bit longer than I planned. So let's see how we do that in a system. So here we have a system of equations. I'm going to write my coefficient matrix based off of the coefficients of A of X and Y. And I'm going to write my right-hand side matrix based off what's on the right-hand side. Okay. In order to use inverses to solve, I need to figure out what A inverse is. So I'm going to take the determinant of that and divide it by 1. And then multiply it by switching the two, the A and the D, and then changing the sign of B and C. So this is my my inverse matrix. And we're going to take this matrix and multiply it times the original B matrix. And we end up with this matrix, which lets us know that our solution for the system is X is -3 and Y is 7. And if you want to solve some practice ones, I'm going to give you the answers in advance so you'll get an idea, so you'll know what to do. All right, thank you.